Hi everyone, I'm Kelly, and I'll be presenting the introduction for the CS6340 Fuzzing Lab along with Matt, so let's go ahead and dive right in. First, the corresponding lecture for this lab is Lesson 3, Random Testing, so I would definitely make sure to watch that before getting started. As you can see from the goals, this lab is divided into 3 parts. In Part 1, you'll be writing a division by zero dynamic analysis for C programs as an LLVM pass. So at a high level, you'll be creating an LLVM pass that will instrument C code with some additional instructions that will perform runtime checks. Your analysis will be providing some code coverage metrics also that will be used in a later part of the lab. In Part 2, you'll be writing an automated tester for C programs that perform basic randomized testing. We've set up the general fuzzer framework for you, but it will be up to you to determine what mutations you want to implement and find out which ones work best. And then finally, in Part 3, you'll be expanding your automated tester from Part 2 to use program feedback, which will be your code coverage metrics from Part 1, to direct randomized testing. So using this, your tester will be smart enough to determine which mutation it should use without you specifying which one. Besides the lecture video, here are some additional resources that you'll find helpful. You can find the links in the resources section of your lab document. The first 3 bullet points are about different LLVM classes and instructions, and that will help you with Part 1. The fuzzing bullet point will be helpful for Part 2, and then code coverage will be helpful for Part 3. So to set up the lab, you will first need to download fuzzing.zip from Canvas and unzip it in the home directory of your VM. Particularly due to the LLVM setup, I definitely don't recommend attempting to do this lab anywhere besides the course VM. And that's also where we'll be grading, so you want to make sure that it runs on the VM anyway. The lab doc has a setup section for each part of the lab. You'll find that the later parts are dependent on some files from the earlier parts. So let's go ahead and get started with Part 1. So I'm here on the VM. I've downloaded the fuzzing.zip. So let's copy that to our home directory and go ahead and unzip it. So that creates a fuzzing directory. So let's go into that, and then we'll see a Part 1, Part 2, and Part 3. Let's go into Part 1 and then follow the instructions in the lab to make a build directory, and then we'll run the cmake command, and that's going to set up our make files and get us ready to run the lab. So here we can see our make file and other build files that were created. Let's go ahead and run make. And just a reminder that each time throughout the lab that you change your instrument C++ file, you'll need to rerun the make so that it picks up your changes. Otherwise, when you're testing, you'll wonder why nothing has changed. Okay, so that's done. Let's go ahead and go into our test directory. And we're going to run a couple commands, the cling to create the LLVM intermediate relation file. Then we're going to run an opt command, which is going to give you an instrumented file. It's basically the LLVM optimizer command, and it's going to load in your instrument C++ changes and insert them into the simple zero program. And then we're going to run the clean command again to compile the instrumented file. And then when you're done, you'll have a simple zero executable that, if everything's done correctly, you'll get this floating point exception. So looking at this code snippet, we can see that we have two potential divide by zero errors, one at line 1 and one at line 2. In the second box, we've added some manual checks to catch this error, but that's a little bit repetitive. So expanding on that, here we've encapsulated the check into a sanitizer function that we can reuse. So every time that there is a division instruction, now the sanitizer is called to do the check. But for this lab, our job is to automate inserting these checks at the LLVM intermediate relation level using an LLVM compiler pass so that they don't have to be implemented at the source code level. Going back to the commands that we executed during the setup, the first clean command is creating the LLVM IR, and that outputs a simple 0.ll file. The -g option includes some debug information for the LLVM IR instructions, and you'll need to get that debug info for the instructions and send it to your sanitizer so that you can report the location of the divide by zero error. And in the screenshot, this is an excerpt from simple0.ll, and here you can see the call statements with some debug information, and that wouldn't be available if you had compiled without the -g option. So we've set up the framework for you. All of your edits are going to be done in the source instrument.cpp file. You can not edit runtime C, but it will take care of printing the error message with the line and column information if there's a divide by zero error, and it also creates the file with your line and column for your code coverage metrics. So this is the instrument C++ file that you'll need to edit. There are 3 functions that you'll need to complete. Instrument sanitizer is where you'll implement your divide by zero sanitizer and insert the dbz_sanitizer check for a supplied instruction. Instrument coverage is where you'll implement your code coverage instrumentation and insert the coverage checks for all the debug locations. And then lastly, you'll need to modify run_on function to appropriately call your instrument sanitizer and instrument coverage functions. So if you've been following along in the lab doc, the next 3 sections are going to cover inserting instructions into LLVM code, loading C functions into LLVM, and debug locations in more extensive detail. So I'm not going to go into detail on those sections here, but definitely spend some time understanding those and it'll help you a lot. So looking at the example input, your sanitizer should run on any C code that compiles to LLVM IR, which is what the clang emit LLVM command is doing. To test a different program, you'll just need to replace simple 0 with your program name, and you'll only need to do this once for each program. Next, we'll create an instrumented executable using your LLVM compiler pass. The opt command is the LLVM optimizer that's loading in your instrument changes. So you'll need to run this one each time you make changes and build your instrument C++ file. And then finally, you'll run the clang command to compile the instrument version of the program, and that will give you an executable when it's done. So when you run the executable, we'll do simple 0 in this example. If it's correct, it's going to print out divide by 0 detected at line 4 and column 13 for simple, and then the line and column number will change for other programs that you're testing. And then you'll also see a simple 0.cov file created with the line and column information that you can verify against the lab doc to see if it's correct. So that wraps up the overview for part 1. I'm going to turn it over to Matt and he will cover the remainder of the lab.
Let's talk about part 2. We are going to write an automated tester for C programs that performs basic randomized testing. So we are writing a fuzzer. Let's talk about what does a fuzzer do. A fuzzer tries to produce failures in a target program by offering it lots of invalid inputs. Now, you can fuzz for many kinds of failures. In this lab, we are specifically fuzzing for divide by 0 exceptions. So how does our random fuzzer work? that we are building right now. We start with a seed of English text, and we choose a mutation function. We apply that mutation to the seed, we produce a mutant. We feed that mutant into the target program's standard input. Now, the instrumentation you built in part 1 is still in play because it's running in the target program, and our fuzzer knows how to check the instrumentation's output and see if a divide by 0 happened. So that determines if the run was either a success or a failure, and regardless of whether it succeeded or failed, we repeat the process with that mutant as the new seed. So over many, many iterations of slight mutations to the original seed, you end up with something that's unrecognizable. You start with some readable English text, you end up with something very corrupted, and hopefully, in the course of all that corruption, we've exercised lots of corner cases in the target program and shaken out some interesting crashes. Now, the lab PDF suggests several mutation strategies. You only need to pick 3 to actually implement. Now, the grader has some expectations. The grader will try all of your strategies against all of its target programs. Those target programs may include things we've already given you, and they may include things we haven't given you. The grader expects to find at least one crash in every target program. That does not mean every mutation strategy needs to produce a crash in every target program. It means for every target program we give your fuzzer, we expect one of your strategies to produce a crash. Now, let's look at part 2 on the terminal. So I'm going to assume that we've already had a successful part 1. And I'm going to start here from completely uninitialized part 2 directory. So I've got my part 2 directory here. There's nothing in reference, and that's a problem because we need to get part 1 into here. So let's go ahead and copy that. That's the instrument pass. We're going to put it into reference. Okay, now that we've done that, we need to set up CMake. Great, we have a make file. Let's go ahead and make. Okay, now we have our fuzzer. Let's see what it does when we run it. It just tells us about the parameters it expects. Now, let's look at the code we just built. In fuzzer, we have, of course, the main method, and it handles the parameters, and it kicks off the main loop of the program where we're going to take a seed input, make a mutant, run a test, and then take that mutant and push it onto the list of seeds. Let's talk about those mutations. In the skeleton code we give you, these mutations are useless. They take a string and they pass in the same string unaltered. That's not going to get you very far at all. So majority of your work in part 2 is going to be thinking about mutation strategies that we can use on the text to corrupt it in interesting ways and try to shake out some corner cases in these target programs. So let's look at the seed. That is in test. In fuzz input. Okay, this is some easily human readable, comprehensible text. Nothing too interesting going on here. And we'll see how the fuzzer uses it in a second. So now that we've built a fuzzer, even though it doesn't have really useful mutations, we can kind of play with it here. We built it. Now let's give it a run against some of these test programs. Now a great test program here is Sanity, because Sanity always fails. Doesn't matter what you give it. Always fails. So let's fuzz it, just to make sure that the fuzzer is going to do what we expect it to do. So let's make a directory for the fuzzer output, and then let's see what our parameters are. Okay. Fuzzer, we're going to do sanity, read from, oh, there we go. Read from that, output to that. Campaign doesn't matter, we'll call it mutation A. We get lots of crashes. Just a quick control C to kill that. If I didn't want to have to use control C, I could run it on a quick little timeout. Let's do timeout 1 second. There we go. Okay, so what did it produce? It found lots of crashes, so it found lots of failures. Let's look in the output. Oops. Output. Look in our failures. And of course, everything in here produced a failure in sanity. It's not very interesting, but it does prove the point that the fuzzer is doing its job. If I wanted to feed one of these inputs back into the original target program, just to verify the crash really happened as I expect, I can do something like this. Let me go back a couple directories, pick up sanity, and I'm going to read in, say, input 273 mutation A. And of course I get a crash. That's great. There were no successful runs, obviously. Every single run failed, but if I did have successful runs, I would see a sample of them here. Now there are going to be thousands, maybe millions of successful runs, so the fuzzer is only going to write a small portion of those to the success directory, but you'll find them here if you want to see what it's doing when it's not producing crashes. Okay. Oops. So back to part 2. I think that is all we need to talk about in part 2. Now you know how to build it and run it. So let's move on to part 3. Part 3 is going to expand the automated tester to use program feedback to direct randomized testing. So what changed? What are we doing differently? Well, in part 2, there were 2 main ideas, right? We blindly apply a user-chosen mutation over and over to a seed. If you choose mutation A when you launch the fuzzer and you let it run a million times, you get a million iterations of mutation A. Doesn't matter if that's helping explore the program at all, it's just that's what the fuzzer is going to do. And that fuzzer is always going to choose the newest mutant as the seed into the next iteration. Even if that's not going in a fruitful direction, that's just what it's going to do. So part 3, big break. Part 3 is going to require the fuzzer to choose a mutation from those available at every iteration. So there's not going to be a command line parameter to say do mutation A. We're just going to say, hey, start a campaign and pick mutations as you go. Part 3 is also going to require the fuzzer to identify interesting mutants. So what does that mean? Well, it can mean a lot of things, and look in your lab PDF for some thoughts in this area. But let's think back to part 1. One thing we did in part 1 was the divide by 0 sanitizing. But another thing we did was wiring up a code coverage tool. And one view of an interesting mutant would be a mutant that increased the code coverage from the previous run. Even if it didn't create a crash, it just exercised more instructions, and that's profitable. We want to keep going in that direction. Now, if a mutant did not increase code coverage or decreased it, that's not profitable, that's not interesting. We probably wouldn't take that seed and iterate on it further. But the mutant that did increase code coverage, we would definitely iterate on that further. Now, like I said, that's just one view of what's interesting. And look in your lab PDF for more ideas, and also talk to instructors and see where you might want to go with that. So how does this work? What's the workflow here in part 3? Take the seed of English text, choose a mutation of those available, apply it, feed it standard input, check if it produced anything interesting. If it did, that becomes a new seed. If it didn't, keep the seed you have. Let's go to the terminal and play with that for a minute. I'm not going to show you the steps that are exact same as part 2. There's, make a build directory, do your CMake stuff, get part 1 into reference. You've seen that previously. So I just want to talk about the different way the binary is invoked. If I go into test and look around, you can see I've already run some programs here. Invoking it does not include picking a campaign. You can see that in the parameters. So if I want to run a quick test here, build fuzzer, let's do easy, and let's give it the usual seed and the usual output. This is all I need to do. Obviously, my fuzzer should be picking its own mutations as part of its campaign. There's one file here I want to draw your attention to because it's very important for your code coverage work. That is, I've run sanity previously, and it's left behind a nice little file here called sanity.cov. That's straight out of part 1, right? Look into that file. And think about how this can help you. This is a good way to get some interesting information about the target programs. So let's talk briefly about expectations for part 3. This is all about producing the most interesting mutants in the least time. We invite you to reuse your part 2 mutation strategies, although you can also improve them or you can replace them if you want to. The grader will try a single campaign against every target program. Some target programs you have seen and some maybe you haven't. And the grader expects to find at least one crash in that execution. And please refer to your lab PDF for details about timeouts and point allocations and all those good topics. So thank you for watching this video with me and Kelly, and good luck on the lab.